Hello everyone, Teacher Josie here. Welcome to my channel. For today, we are going to discuss quantum mechanical model of an atom. In previous grade, you learned about Rutherford's atomic theory. According to this theory, an atom is mostly empty space and its mass is concentrated in a small region at the center called nucleus. The protons and neutrons are located inside the nucleus, while the electrons are distributed around the nucleus. However, this model could not explain the characteristic color of flame emitted by metals when heated. In this video, you will learn about Niels Bohr's atomic model and understand about the quantum mechanical model of the atom. You will also understand that the characteristics of matter are related to how electrons are distributed inside the atoms. The lessons in this video are aligned in the learning competency. Explain how the quantum mechanical model of the atom describes the energies and positions of the electrons. There are two lessons in this video. Lesson 1 talks about electrons and energy level. Lesson 2, it talks about electron configuration. At the end of the Lesson 1, you will be able to relate colors of light emitted by metals to the structure of the atom. Infer that electrons can stay only in definite energy levels. Identify the energy levels, sublevels, and atomic orbitals in an atom. Determine the maximum number of electrons that can stay in an energy level. Have you observed the different colors of light emitted by these fireworks? Do you know what is responsible for this array of colors? Would you believe that this is due to the arrangement of electrons within the atoms? Excited to discover more about the atom? Let's go! Firework effects are produced by the combustion of explosive materials present in fireworks. These explosive materials are also called metal salts. Metal salts emit characteristic color of light when heated. The following are the color emitted of some metal salts and its element responsible for its color. Sodium nitrate. The element giving color is sodium. The color of the flame is yellow. Barium chloride. The element giving color is barium, and the color of the flame is green. Barium nitrate. Again, the element giving color is barium, and the color of the flame is green. Calcium chloride. The element giving color is calcium, and the color of the flame is orange. Copper chloride. Element giving color is copper, and the color of the flame is blue. Lithium carbonate. The element giving color is lithium, and the color of the flame is red. What can you conclude about the elements and the color of flame produced? The answer is, each element produces its own characteristic color. If sodium nitrate is changed to another salt of sodium, example, sodium chloride or table salt, do you think the color of the flame would be the same or different? Why? The color of the flame will be the same. It is sodium atom that will give color to the flame. Here are some chemistry of fireworks. Each color of light has a specific wavelength. Among the visible light, red light has the longest wavelength and has the lowest energy. Violet light has the shortest wavelength and has the highest energy. When compounds of different elements are heated over a flame, it comes to a point where the hot gaseous atom begin to emit light of a definite color. Analysis of light given off by the vapors of elements can be done more precisely with an instrument called spectroscope. With the use of spectroscope, one can detect a series of narrow lines or line spectrum on the light given off by an element. The spectral lines suggest different energy levels in an atom. How did Niels Bohr explain the spectral lines of an element shown in the spectroscope? Each line in the atomic spectra of elements suggests definite energy transformations within the atom. Bohr stated that electrons are moving around the nucleus in a circular path or orbit at definite distances from the nucleus. This is similar to the planets revolving around the Sun. Electrons in each orbit have definite energy. This energy increases as the distance of the orbit from the nucleus increases. These orbits are also known as shells or energy levels and are assigned each a number N1, N2, N3, and etc., or letters K, L, M, N, O, and etc. As long as the electron stays in its given orbit, there is no absorption or emission of energy. If the electron received extra energy, it can jump into a higher energy level. This is also called excited state. The electron in the excited state can return to its original lower energy level or ground state by releasing discrete amount of energy in the form of light. This atomic model presented by Bohr is comparable to a staircase as shown on the figure below. When you walk up or down the stairs, your feet must hit the steps, not on the empty space between each steps. Otherwise, you will be in trouble until you hit another step. The higher you climb the stairs, the more energy you need. Similarly, the electrons can only stay in a definite energy level and not on the space between energy levels. The farther the energy level from the nucleus, the higher the energy. Similar with the electron, what does the man require to climb up the stairs? It needs energy. When going up the stairs, is it possible to reach the top instantly? Represent man as electron when explaining. It is not possible. What happens to a person attempting to step on the next level with insufficient energy? The person cannot climb to the next step. Can electrons occupy any space between energy levels? The answer is no. An Austrian physicist, Erwin Schrödinger, together with Werner Heisenberg and Louis de Broglie, made a refinement of Bohr's atomic model. Schrödinger used mathematical equations to describe the possibility of finding an electron in a certain location. Heisenberg discovered that for a very small particle like the electron, its location cannot be exactly known and how it is moving. This is called the uncertainty principle. De Broglie proposed that the electron could also be thought of as a wave. Based on the quantum mechanical model, it would be impossible to plot a definite path or orbit for the moving electrons. At least, we can only guess the most probable location of the electron in a given instant to be within a certain volume or region of space surrounding the nucleus. An atomic orbital is the region around the nucleus where the electron is most likely to be found. The atomic orbital serves as the house of the electron. The maximum number of electrons in the main energy level is determined by the formula 2n squared, where n is an integer that designates each energy level. For the first main energy level, K or N1, in the second main energy level, L or N2, in the third energy level, N is equals to 3, and so on. For the first energy level, N is equals to 1, the maximum number of electrons in the first energy level is 2. For the second energy level, N is equals to 2, the maximum number of electrons in the second energy level is 8. For third energy level, N is equals to 3, maximum number of electrons in the third energy level is 18. For the fourth energy level, N is equals to 4. Maximum number of electrons in the fourth energy level is 32. Each main energy level contains sub-levels, and each sub-level has a fixed number of atomic orbitals. For the S sub-level, there is only one atomic orbital. P sub-level has 3 atomic orbitals, and D has 5 atomic orbitals. Let's proceed to the lesson 2. At the end of the lesson 2, you will be able to determine the pattern of filling the atomic orbitals based on the given electron distribution of the first 10 elements. Write the electron configuration of the elements in the third period of the periodic table. Tracking down the location of a given electron in an atom is similar to tracking where a person lives. To find this person, you need to know his complete home address, city, barangay, and the house number. This corresponds to energy level, sub-levels, and atomic orbitals in an atom. In order to track where all the electrons in an atom are, chemists use notation called electron configuration. This electron configuration is the most stable arrangement in which the electrons have the lowest energy. An example of electron configuration is 1s2, 2s2, 2p6 for neon atom. Do you know how this electron configuration is obtained? You will find out in this lesson. In the electron configuration of 1s2, 1 refers to the main energy level occupied by the electron. S denotes the kind of orbital, and the superscript 2 for the number of electrons in the orbital. The main energy level also tells us the number of sub-levels, and the name of the sub-level is also the same with the name of the orbital. There are 3 rules are applied in deriving the electron configuration. These are Aufbau's principle, Pauli's exclusion principle, and Hand's rule of multiplicity. For Aufbau's principle is also known as the building up principle, states that electrons occupy orbitals in order of increasing energy. It follows this mnemonic in filling up the orbital. First, 1s, next is 2s, next is 2p, next is 3s, down to 3p, then 4s, down to 3d, 4p, 5s, down to 4d, 5p, 6s, down to 4f, 5d, 6p, 7s, down to 5f, 6d, 7p, and 8s. Let's have an example. To find electron configuration is to find the number of electrons for the element, and we're going to look at the number above the element symbol, which is called atomic number. It will tell us the number of protons as well as the number of electrons. So we'll try an example with boron. You can see we have this chart here, and this is the general format. We know we have 5 electrons, so we'll follow the chart and we'll go down with the 1s. So we write 1s, and we know that it holds up to 2 valence electrons. Then we have the 2s, following the arrow down, that holds 2 electrons as well, since it is s orbital. We have 5 electrons in boron. Then we go down this row here with the 2p and the 3s. We only need 1 more electron to get 5. We know that the p holds up to 6 and we need only 1. So that's our configuration for boron. 1s2, 2s2, 2p1. Notice that the numbers add up to 5, just like the number of electrons for the element. The second is Pauli's exclusion principle. Electrons occupying the same orbital must have opposite spin. Consider the electron configuration of lithium, 1s2 and 2s1. The orbital diagram we have here, 1s has opposite spin. 2s has only 1 because there is only superscript of 1. Next, consider the electron configuration of sodium, 1s2, 2s2, 2p6, and 3s1. The orbital diagram of 1s, there are 2 arrows with opposite spin. 2s, opposite spin. 2px, 2py, and 2pz has 2 opposite spin. And 3s, there is only 1 arrow. Did you understand now? Here are some examples. Do you see any pattern in the electron configuration of the elements? Yes. What are these patterns? Electrons occupy orbitals in order of increasing energy. There are 2 electrons occupying an orbital with opposite spin. An orbital in the same sublevel is filled with 1 electron of the same spin before pairing. The third is Hand's rule of multiplicity. When electrons enter a sublevel with more than 1 orbital, they will spread out to the available orbitals with the same spin before pairing. Consider the following configuration of nitrogen, 1s2, 2s2, and 2p3. The orbital diagram goes like this. For 1s, there are 2 opposite spin. For 2s, there is also opposite spin, while the 2px, 2py, 2pz has 1 arrow, meaning to say they will spread out to the available orbitals with the same spin before pairing. Let's have an activity. Write the electron configuration of the elements and show the orbital diagram using the Hand's rule and Pauli's principle. Do you have the same answer? In summary, Bohr's atomic model describes the atom like a solar system, where the electron is found only in a specific circular paths or orbits around the nucleus. Electrons in each orbit has fixed energy. An electron can jump to a higher energy level by gaining energy and return to a lower energy level by releasing energy in the form of light. The Bohr model was later replaced by a model of the atom that show that electrons are not limited to fixed orbits around the nucleus. Schrödinger formulated a mathematical equation that describes the behavior of the electron. The solution to the equation is used to calculate the probability of finding the electron at a particular region in space around the nucleus called atomic orbital. The quantum mechanical model of the atom describes the atom as having a nucleus at the center around which the electrons move. This model describes a region in space where the electron is most likely to be found. The distribution of electrons in the different atomic orbitals is called electron configuration. That's all for today. Thank you for watching. See you again in the next video. Don't forget to click like, share, subscribe, and click the notification bell for more videos. See you again next time. Goodbye.